we're going to be looking at a robot that I haven't spent a lot of time looking at before. So I want to see how a design exploration works with a robot I haven't seen in person. And we're going to talk through it a little bit. This robot was posted back in April by 2220. Blue Twilight out of Eagan, Minnesota. And really, I found it looking through. I had seen it before when they posted it on Chief, but I also found it looking through our CAD collection. They had submitted it here, and I was looking for a 2020 robot to look through. So we can see kind of how some of the infinite recharge robots were built. If anyone is interested in looking through more robots and doing it on their own time, this is definitely the easiest way to do it. If you just go to cadcollection.spectrum347.org, it'll bring up this whole list. There is a huge number of robots, some of them old, some of them new. It's something like 525 robots now. Tons of robots, also a bunch of tech documents, so you can go through and look at kind of like the posters and things that people build for the judges that explain their robots too. So if you just don't want to look at the CAD because it's sometimes hard to figure out what's actually going on, a lot of these tech documents are really nice for seeing exactly why teams designed what they did. So these are also all included in here. And I was looking through some, I went through and I was just kind of looking through the robots and I saw Blue Twilights, and they did a really good job of building a relatively simple robot that was able to accomplish basically every game task. So this is what it looks like, the actual full robot, or most of it. I don't think the climbers are mounted here. This team did not get to compete in 2020. So we don't have any match video. We don't actually know how well the robot performed, but we can see a lot of their design intent by looking through their CAD and seeing how they went through and designed everything. They had, so we can start kind of bringing out through the full on-shape window here. So a lot of the design principles they used are similar to a lot of robots in 2020. They're a lot similar to the robot that Spectrum built, also similar to a lot of the other robots that are also in the Open Alliance. So there's a lot of information published every season by teams who are just looking to help other teams. They're open about how we're going through our design process, what works, what doesn't. And a lot of teams kind of had, a lot of the Open Alliance teams kind of verged on a somewhat similar structure. The robot had, most of the Open Alliance robots are sort of the normal skid steer or tank drivetrain where you have a left side and a right side, and you power them individually and you can make the robot turn. The kit chassis, so this is actually one of the really nice things about the Blue Twilight robot is they actually are using the kit parts AM1ForU4 chassis. So we did a whole presentation on that earlier and dug through exactly how all of that works. And then they have a simple roller intake, very similar to a lot of the other robots in the Open Alliance, and we'll look through how that works. And then they also have one of these V funnel concepts that a lot of robots used in 2020, just to sort the balls. And then they decided to be a tall robot. So that's where a lot of 2020 robots differ. You can either be tall or short. So if you were short, you could go under the control panel. If you were taller, it meant that you had a little bit, you had basically like a less distance to shoot. You didn't have to raise the ball as high. And you also had a little bit easier time packaging the climber mechanism as well. So we have the tower that kind of feeds the balls up into their shooter mechanism, which is in here. And then we have the climber, which are these two posts and the motors and things down below it. A lot of what we're going to look at is kind of how they actually designed to build it, what they were able to do in relatively simple design process, but building a very complete robot. So starting down at the drivetrain, we can actually flip over. So in Onshape, you can kind of, everything's done in subsystems here very cleanly. So we can flip over and we see just the drivetrain. And so there's really nothing special here that any team couldn't do. So this is the kit parts AM1ForU chassis. It's the same chassis that we use on, that they use on the Everybot. And so the Everybot that we build uses the same chassis. So a lot of teams are very familiar with it. They even use the same, the kit battery holder. So all of that's kind of just ready to go. they do upgrade it in one way. So instead of using the sim motors, they use Neo brushless motors. So their drivetrain is going to have a little bit more acceleration and a little bit more pushing power than a robot that's just using 4 sim motors. And this gets you a very, very good drivetrain. Like it's a top percentage drivetrain in FRC just by switching to either Neos or Falcons or one of the 2 brushless options. You don't have to replace the gearbox. You don't have to do anything else. You just get the right. For Neos, you just can use the same pinions. You'll be probably a little bit faster than you were with Sims. But overall, it's a very good upgrade and it's very inexpensive. It's very reliable and it just sort of works. And it looks like from everything else, at least in CAD, they didn't really do anything else to it. They look like they followed they didn't really modify basically the entire kit chassis and left it all alone, which is completely reasonable and it works and it's great. And you can have a very good robot doing that. Let's see, coming up from that a little bit, we'll start, I guess, at the front of the what's known as basically the ball path, right? How does the ball move from the floor and how does it get out of your robot going towards the goal? So the front of the ball path is going to be the intake. I don't know if this is, again, I'm looking at this basically for the first time too, so I don't know the entire organization of their robot. We may not be able to see that subsystem. I can probably pull it somewhere in here. Power cell manipulator. Oh, okay, everything's kind of built in as one subsystem. Yeah, it looks like. Oh no, there's an intake. All right, so we can switch over to intake here. Okay, so this is like the intake just broken out fully by itself. We don't know some things like material. Sometimes you can go back and look at photos and kind of see. So this was polycarbonate in this version. I don't know if they had plans to upgrade it to something or to change it to something else. Polycarbonate definitely works. It's the same thing. It's what we use on our intakes. It's very useful when you're sticking it outside of the frame perimeter because if it's very impact resistant, so it's not going to bend easily if it gets smacked by another robot or if you run it into a wall. So polycarbonate is very common for intakes. It's black here in the CAD, but it's very possible, like just like in the real robot, it's clear. So this was likely made on a CNC router. You're able to just you do the CAD, you get all of the holes placed, and you have it route out the part, drill all the holes for you, and everything is nicely done. It's possible for teams who don't have a router or a big enough or some other way to make the part, like a laser or something like that, our team would probably laser cut this part, depending on how big it is. And so it's about 14 inches. So it's pretty large, but you could almost certainly print this on like a legal size paper where you have like 11 by 17 or something like that. And you could get, you could basically make a 1-by-1 copy of this and make kind of a template, go through, drill the holes based on those marks and cut it out and get something pretty close. So for teams who don't have CNC tools, there's definitely a way to make a part like this. The actual intake itself is 3 rollers. So you have these rollers with the black rubber right here. Those 3 are the ones that are actually contacting the ball. And those are the ones that are spinning the whole time to bring the ball up over the bumper and into the robot. These other 3 tubes, these are just stationary. So they're acting like standoffs and they just provide rigidity to the whole assembly so that it doesn't just wobble around and you can keep basically the distance between these plates the same even when it's getting run into things. And that way you don't have problems with like your belt distances changing or anything like that. Okay, let's look at kind of how the power actually gets transferred. So we start up here. They have 1 Neo running their intake. So this is just a Neo motor. They have a pulley on the end of the Neo. In the CAD, there is a 1/2-inch hex pulley. So they either So, and then there's the output of a Neo is this small 8mm round shaft that has a key in it. We talked about that when we talked about the Sims. It's that same output shaft. So somehow they have to adapt these two. So either they may have like printed a pulley that had a 8mm circle with like the keyway slot in it and used a printed pulley, which some teams can do. You normally don't want to do that necessarily in 3D printed parts. You can, but the key doesn't transfer torque to a lot of plastic, so it's possible it can like mess up the pulley and stop and like kind of break off some of the plastic, and then it's not as good. So more than likely they used an aluminum adapter in here. So there's a couple Vex Pro and Andy Mark both sell adapters that let you have a little piece of aluminum that basically has the key in it, and then you have a 1/2-inch hex on the outside, and you can drive the pulley that way. And that's more than certainly what they probably did and just didn't include it in the CAD. To mount it, they have the spacers here and this spacer plate. And so the bolts, these 3 bolts just go into the 3 bolt holes of the Neo. This is one of the nice things that the Neo has compared to a Sim or a mini Sim that only has 2 mounting bolts. You can have this 3rd mounting bolt basically up top away from where the belt has to exit. So you can't use the 4th one because the belt's going to basically kind of be in that space. So you have a belt running down around here. Like you might be able to do it like around the belt or something, but that's more complicated than you probably want to do. But these 3 make it so that the motor itself doesn't flex as easily. If you only have these 2, like you would on a Sim or a mini Sim, or sometimes even if you had a Versa Planetary in the same configuration, as this belt kind of gets tight and there's nothing really supporting this end of the shaft, this whole thing wants to start tipping in. So like this point of the shaft will start trying to bend down this way, and this back end of the motor will trying to push up this way, because you kind of get you have a line here that can kind of act as a pivot line or a fold line. But the Neo helps solve that, as you have this 3rd bolt that prevents any of that flipping or twisting of the motor. So we've done this 2 years in a row on our robot. We normally have a 3D printed part that fits there. But this setup with spacers and this extra little plate probably works just as well as our 3D printed spacer that we use. They are using belts here. So they have, this is a 5mm HTD pulley. So you can see that's the kind of standard size FRC belt for the most part for any like larger applications. These are the belts that get used everywhere. They have, these ones are a little thinner than what you find on the kit parts drive chassis, which we looked at earlier. Those are 15mm wide. These are 9mm wide. So when you have a thinner belt, you're able to transfer less torque, but you get the advantage of having less space taking up, right? If they used 15mm here, basically this pulley would have to get double in size. So you'd have less room for kind of like the ball to actually be brought into the robot and things. So the thinner belts here make sense. You don't need a ton of torque to bring the ball up into the robot. You're probably not going to be slipping or breaking these 9mm belts at all. So this is totally fine in this application. The advantage is the 2 of the 9mm belts fit on a 15mm pulley. So if you're buying aluminum pulleys from Andy Mark or Vex or anywhere, and you have the wider pulley, basically the way they design the pulleys in FRC, they can make 2 of the 9mm belts fit on the 15, even though 9 plus 9 is bigger than 15. It all just works out in the sizes that they actually use. So it's definitely an advantage when you're trying to connect multiple things together as they're going from the motor to the roller to the next roller and down again. All right, so how do they do the roller construction? So one of the nice things about a lot of these intakes is you kind of, once you figure out how to do one, you kind of just copy it again, right? So we can look at this top roller and see how it's mounted and assembled, and we can pretty much assume, and by looking at it, you can tell they're all the same, right? So you can make spare parts really easily, because if you need 3 rollers on your robot, you could have 1 or 2 entire extra rollers in case something happens, and they're all the exact same. They have the same length. It's super easy to make spares. If you have a practice bot, you're making the same ones over and over again. So being able to do that in a design where you're kind of keeping that same part, but you're just using it multiple times, is very useful. So you don't have to have a separate thing to manufacture. You don't have a separate thing to make sure it works. You can just use the same part over and over again. So the way that they built these is with, let's see if we can hide a few parts. So we're going to hide the pulley real fast so we can see the hex shaft in here. I can actually, let's see, I'm going to hide the rubber. So there's rubber on the outside. And then there's this aluminum tube that I'm going to make transparent. All right. So they used VexPro VersaRollers, which is a system from VexPro, which we can actually look at here in a second. VexPro being one of our vendors for VersaRoller. And they've had this for a few years. They've had this system. Some of it was based off of things that West Coast Products started selling a few years before Vex had them. They had a few parts, and then they kind of added and completed the line. That's the picture I'm looking for. And it lets you very easily make rollers out of 1.125 inside diameter tubing. So all of this aluminum tubing that the roller actually is on, this aluminum tubing in here, let's see, this aluminum tubing has the same, has a 1.125 inside diameter. So then they sell these little plugs that, oh, I need to exit, sorry. They sell these little plugs that fit inside of it that then have the hex opening, and you can bolt right to it. So this little plug slides inside. You can drill holes in the aluminum to bolt it to it. So now when the plug spins, the outer roller spins. And they also sell little inserts that allow you to kind of change how these mount to your actual roller system. So you can either put a hex shaft all the way through it if you want, or you can do what Blue Twilight does here. And they use where'd the little shaft go? That's confusing. Okay. They use this little plug right here. I'll look at the second one because it vanished on the other one. They use this little plug that has the hex and this little ring to stop it from sliding too far into the plug. So it kind of fits right on, it fits in a little recess in the plug for it. And then it has a tapped hole for this shoulder bolt that's on the outside here, so it can fit through the bearing. So the hex shaft itself doesn't go through the bearing. The shoulder bolt kind of tightens in and squeezes the end of the hex shaft up against the bearing. And then the shoulder bolt is what's riding inside of the bearing. So this is what the shoulder bolt looks like. This part down here is threaded like a normal bolt. This part up here is basically a really smooth, round, basically just a shaft. So instead of trying to spin on the kind of uneven threads of a bolt or anything like that, you have the actual smooth shaft that's going to fit really nicely inside the bearing and allow everything to spin. So the outer side of this bearing is going to be stuck into the plastic. It's not going to spin. The inner part of the bearing is going to spin along with this bolt and along with the rest of the roller. They do the same over on this other side, except they don't need the pulley. So everything gets a little bit more compact over on this side. So this plug is just a little bit smaller. So it doesn't have this other hex shaft. It does have a little bit of it has a snap ring groove here, which is one of the ways we retain things to shafts. So you'd have a snap ring on this end, and that would stop it from going in or out of this end of the roller. And then it has the same end here to be able to bolt right up into, right up with the shoulder bolt and the bearing, and kind of complete the roller system. All right, let's unhide some things. Cool. Okay, so and there's a couple different ways you can do it. They sell longer ones, so if you do need double pulleys, you could do that. If you wanted to stick a hex shaft all the way through it, you could do that. It just kind of depends on what you need. They also do have metal and plastic versions of this. So in lighter duty applications, you can use a plastic one. It is possible to like print your own if you wanted to for some of the light duty stuff, but the molded ones are pretty cheap. You can see the different prices up here. Yeah, the plastic ones are $4 a piece, so they're not bad. Even the aluminum ones are $5. So they're pretty inexpensive. The inserts are too, so there's no real reason not to buy them if you don't have the ability to make them or the bandwidth to make them. It's totally fine to buy things like that. And they basically just repeat that process 3 times for the 3 rollers. The kind of last part of their intake are the standoffs. They use these in a few other places on their robot as well. They are, according to this, 885 OD tubing, which is likely 7/8, which is 875. So you have this aluminum tubing running the whole length of the intake, which you can see here. It's this gray tube, and inside of that, the way we connect it to the plates are with tube connecting nuts. So we use these a lot on Spectrum robots. They're very helpful, and they're basically this little part right here, these 2 sort of bowed out pieces and this round kind of center. And you basically can shove these into the end of the tube, and this flower part, it'll deflect as it's going in, but then if you try to pull it out, these steel sides in here kind of dig into the walls of the tube and they don't let it come out. So that lets you tighten it up to, as you bolt in, it basically tightens up and it sinks in, and it won't let these inserts come out at all unless you have an extreme amount of force pushing them out. We've never had one come out that I know of, not on an actual competition robot. They're relatively easy to get. We get them from McMaster. McMaster being a very common part source for a lot of FRC teams. Tube, what is it? It's tube connecting nut, something like that. Tube connector nuts. There we go. Nope, tube connecting nuts. All right. So yeah, so there's a bunch of different sizes depending on the tube inside diameter that you want. So you can look at what the tube inside diameter is, match it up, and get the correct tube connecting nut for them. They are relatively inexpensive, a little over, a little under $1 a piece for most of the sizes. Yeah, somewhere in there. So not too expensive. You don't want to be breaking them constantly, but we definitely use them a lot as they can save quite a lot of weight instead of having a solid aluminum bar going all the way across or something like that. So here you get a really thin wall aluminum tube that provides kind of the rigidity and structure that you need without all of the extra weight, because you don't have anything kind of in the middle where you don't need it. You just have the material over on the end, and that's all you really need. There are other kind of the other ways to do the same thing. There'll be some teams who, instead of using the tube connecting nuts, they'll make their own plugs to go into the end of the tube. So similar to kind of what the plug over here looks like a Versa plug, where you'd have like an aluminum plug with a tapped hole in it, and you shove it into the tube, whether it's a press fit or you did something like here where you bolted it in. But it just requires a lot more manufacturing. You're probably going to add, it might be close on weight depending on how big you make it. But for the most part, the tube connecting nuts are so simple. You can buy them, they're cheap. So we end up using those instead of trying to make our own plug basically ever. And that pretty much sets it up. They do have to, since they did use belts here, you do want to make sure you're doing a good job of running, figuring out how long the belts you need are, and you have to figure out exactly where your rollers are positioned so you get the right length. If you get those calculations wrong, the belts won't have enough tension in them. There won't be like stretched the right amount. They'll be too tight, which makes it hard to spin the rollers, or they'll be too loose and the rollers can slip. So you do have to run it through a belt calculator to figure out where your rollers need to be for the belts you're using. And there's a couple different ways to do that. There's several YouTube videos on it as well, and how to figure that out. We're not going to go too deep into that right now. That'll take a little bit too much time. Let's back up, and we can look at what they're calling their hopper. That's just some boxes for it. Let's back up all the way to the top level assembly, and we can see where the hopper is. So the hopper is basically there just to sort the balls into their tower. Maybe. Okay, we can do it this way for now. So we can see roughly how this panel works. They basically have a flat bottom, so the balls come up from the intake, get to the flat bottom that is their kind of hopper floor, and they have these two belts that form a V that funnel the ball into the tower or the structure or whatever we want to call it. Okay. There we go. So this is a relatively easy subsystem. It definitely takes a lot of testing. I think there's a lot of teams had different versions of this V funnel style thing. And it really just depended on what your specific kind of robot requirements were. So some of them were sort of taller or shorter, or the belts were longer. And the V, what angle this is at compared to here, kind of compared to the straight lines, were all sort of different. And that's where a lot of testing comes in, and kind of packaging and just making sure you can fit it into your specific robot. But the concept is pretty much the same on all of them. And you just have these angled belts. If you have two balls, one of them gets selected to go in and the other one kind of stays out here. So there's a couple different ways to do that. Teams ran them either at varying speeds. So some of them had like one side going faster and the other side going slower, but they were both kind of pushing the balls in. There also were teams who had one side going backwards. So you had one side kind of pulling a ball out while this side was pushing the ball in. Or you'd have variable control between them. It kind of just depended on your specific setup and what testing showed sort of worked for you. Most of the time on our robot on Spectrum, we had them both driving in. One was just faster than the other. And that seemed to work for us. We did have some unjam modes where we could run them both backwards, or we could do things to kind of, if something did happen and we needed to clear a jam because the balls got stuck together, we had ways to do that as well. Again, they use kind of the same parts, right? So this whole side assembly over here is basically the same as this one. Everything matches up. It's just symmetrical. So if they can make one properly, they can make the other. And they have spares for everything just by flipping things around. Here is a 775 Pro motor going into a VersaPlanetary. We talked about VersaPlanetaries last week. This is a really simple way to get the right gear reduction, so you can get this belt set up spinning at the speed you want, and you can adjust it throughout the season by changing these gear ratios if you need to. They have it just mounted straight to this piece of likely polycarbonate. And then I'm assuming there'd be a belt and pulleys that would attach here, and that's how they would drive this belt and start pulling the balls in. The rollers are relatively simple. They are just hex shaft, or specifically thunder hex shaft. These are thunder hex are the ones with like kind of the rounded corners. And then hex bearings or thunder hex bearings, really just depends on what they want to use, on the top and bottom here. And then some way they'd have a way to retain the hex shaft that we're not really seeing, right? So likely they either have a, they probably have a bolt up here or something like that with a washer on it, making it so that the entire hex shaft can't just like fall towards the floor. And they also probably have something on this end, either the pulley with a bolt and washer on this end, maybe a shaft collar. There's some way so you can't just like lift this whole shaft up towards the ceiling either. You always want to make sure you properly retain shafts if you have them running through bearings. And then on here, they just have some spacers to keep the pulley in the right spot. Nothing too complicated. They have this extra wide pulley, so it's likely that this is 3D printed. That's what we did for ours when we used these wider belts this year. There's not, I don't know if there's any easy COTS option for a belt this wide. This is probably, what, 1.128 inches, so it's probably like 30 centimeters. Sorry, millimeters. Centimeters would be a big belt. And so it's likely that they 3D printed these pulleys. They may have 3D printed a bunch of the other pulleys on the robot. We print almost every pulley, and thus we eventually make it fail, then we'll maybe move to aluminum, or if there's some area we just want to be extra sure, we'll use aluminum. But a lot of times we'll print our pulleys, especially in these kind of lower load situations. And then it's just driving another shaft over on this end. They decided to build it the same way, even though this one doesn't have to have any sort of hex shaft coming through it at all. So they could have done something similar to how they did the intake and had smaller bearings or something. But if you already have, if you're already kind of using one design method over here, it makes sense to kind of continue it over on this side too. It just makes it easier. You kind of get the same, build techniques going throughout an entire subsystem. And then again, they have the same standoffs that we saw earlier on the intake. They used them again, so they needed some rigidity here to make sure the top of this plate sort of stayed parallel to the bottom down here. So they put in these 3 posts, and they just used tube connecting nuts and cut aluminum tube in the same way as they did before. So nothing too complicated there. The ball tower. So there is probably some stuff that's missing. There's things that are missing in ARCAD all the time too, but one of those is there's no like floor down here. So as the balls let's see if I can get the best view of it. So as the ball comes in, it hits these 2 belts, it gets sucked in by this wheel. So this will be spinning this way and kind of trying to bring it up this path. Right now, the ball would just fall down and like hit this motor probably, or fall into this gap. It's very likely there's some piece of polycarbonate here. We have a little piece of polycarb on our robot that handles that. We actually forgot it when we took our robot to test one day and had to like make a new one at somebody else's shop. We were at Paradox's shop. Thank you, Paradox, for loaning us some Lexan to fix that. So I definitely understand how you wouldn't necessarily have that in CAD. It's a relatively simple thing. It's literally just like a square of Lexan or a rectangle of Lexan in our robot that gets Velcroed down. So it's easy to forget to actually CAD it. So yeah, as their tower works, they have these 2 balls at the bottom. They have these compliant wheels. These are wheels that have the cutouts in them, so that the wheels themselves are able to kind of squish. So you're not just relying on the compression and kind of squishability of the game object. The balls squish too, so it lets it grab it really well. They did that on all 4 down here, and that's what brings it kind of up into these belts that take it all the way up to the wheeled launcher up at the very top. This was done really simply. They actually just had the VersaPlanetary mounted directly in line with this bottom hex shaft here. We can look inside and see how they made that extension. So they used the VersaPlanetary female universal output adapter. So it lets you take a longer hex shaft and put it in here, tighten this set screw down on it, and it makes it so it can't slip out. And now they can spin this hex shaft with these wheels and this belt on it directly from the output of this VersaPlanetary. So they can make that really easy and really convenient. And they just had to cut the mounting holes into this tube for the VersaPlanetary. So they just got the right bolt mounting places for it. And that was all they really had to do. So nothing too complicated there. And then they have the hex shafts at the end that basically hold that hex shaft in place so it can't slide either direction. They make sure to put the bearing flanges on the inside here so your bearings aren't like falling out into the tube. That would be not fun if that happened during a match. Then you see more of the tube connecting nuts and aluminum tube going all the way up, providing some more structure inside of these two beams so they can't flex or twist at all the way up to, again, another hex shaft just going through some hex bearings and a pulley, spacers on it, kind of using the same design techniques all the way through their ball path and making it really simple. They had to be a little bit different over on this side. So instead of direct driving it, let's see if we can get them both in the same picture. Probably not. So this one, like I said, it's direct driven right to that shaft. This one, they couldn't do that as easily, right? Because if they did, they may have even started that way, right? They kind of have all that same mounting holes there ready for this. But their climber, which we'll get to in just a second, kind of takes up part of that space. So it's very possible that the original design, or at some point the CAD, had this motor and gearbox mounted right here, and it was sticking out just like this one is. And then they realized, ooh, we need to get that space back because otherwise we're going to be hitting our climber. So they made a slightly different plate. So this mounting plate here on this side, sorry, let me skip back over, is different than this mounting plate. They added a little bump out, and they added a place to mount the VersaPlanetary here. They added a pulley. There would be a pulley on the end of this VersaPlanetary, and you'd have a belt connecting them. So again, they would do the same. They do some belt calculations, make sure they get the motor the output shaft of the gearbox the right distance away from this shaft, figure out what belt they were going to use, and they would basically be able to power that really simply. And it's a good thing about like iteration or adaptability. It's possible they caught this super early and never really designed this. They may have had this here for some other reason. Maybe in the future they might want to go back to that. Who knows? But either way, they had to do something slightly different, but it definitely doesn't hinder or really even change all that much about how the subsystem works at all. All right, we can go up to the shooter or launcher really quickly. This kind of all happens at the same. Balls come up this tower. I don't see anything in CAD that talks about like how they're going to sequence the balls or control them, but it's very possible they have some sort of sensor in here that's going to figure out how many balls are up in the tower and in what order and spacing. Like there's lots of different ways to solve that problem, and a lot of times that isn't going to be shown in the actual CAD model. It may not, like if there is a sensor mount, it may have been designed somewhere else into it. It may be small enough to where I just don't even see it. There's lots of ways to sort of solve that. Their launcher that they built is just a single flywheel launcher. So they have the single shaft with these two 4-inch launcher wheels on them. Let's see. We get Hexbore 60A. Yeah, so these are the West Coast products, solid rubber wheels. Similar to the Fairline rollers or conveyor rollers that a lot of teams have used for launcher wheels for quite a few seasons. You can get them from McMaster Car or Fixture Works, but the West Coast Products ones are great because they already have a hex hub already through the middle of them, so you can just mount them straight to a hex shaft, where if you get any of the other ones that are designed kind of for industry, you have to do your own adapting. So the West Coast Product ones work great for that. They're super simple and super easy to use. And then they have pulleys on the end of these two Falcon motors up here. So these are the Falcons that they're using as their launcher motors. They'd have a belt connecting from here to the launcher shaft on both sides. And then that would be spinning up their wheels as the ball comes up from their kind of conveyor, their tower, whatever you want to call it. Ball gets launched out the top. The way they're able to set the angle and kind of trajectory of the ball is they have these rods and this hood back here that they kind of built. It appears to be a single position, so you wouldn't be able to like change the position of the hood during the match, which is totally fine. The Spectrum's 2020 robot was the same way. And it's very possible that they would have put some sort of like thin piece of polycarbonate here to kind of smooth out this path. Right now, the balls would be hitting all of these little hex shaft standoffs. It's very likely they have a piece of like polycarbonate either zip tied or attached to here some other way. So that's what it was rubbing against on the backside. I don't think you can, you might be able to see, I don't know if you can see any polycarbonate there on the photo. And then it looks like they did try to figure out a way to build in some amount of adjustability. They had these extra planks here that was with holes on an arc. So maybe they could unbolt and kind of move these up a hole and you'd have a little bit longer hood. So you'd have like a lower launch angle, or you could move them back and have a higher launch angle. These are pretty steep. If you were moving between these two, you'd have pretty dramatic changes in how the ball exits. That was one of the things we struggled with this year, was figuring out exactly how to dial in that single launch angle. It definitely was a little bit, it was more complicated than we thought. We had a bunch of different kind of options and we did a lot of testing, and it was all the way till pretty close to the end of build season before we kind of got something that we were happy with. And I think even then we would have been changing it pretty regularly throughout the season had the season continued. And then the last part of their robot, which I don't think they completely finished because it's not even mounted here, but they may have had it done and just not mounted, is their climber. So we can see we have these two posts here and we have these inside tubes here. So they basically have telescoping tubes. And they're both exactly the same. So in here, they're not even mirrored. So I don't know if they would mirror them in real life, but they have the hooks on the same side here. It's very possible they get mirrored in real life. And so the way a lot of climbers work is, since you're only really having to exert a lot of force when you're actually trying to pull the robot up and kind of do the chin up motion. That was the end of this game, right? We had to grab the bar that's kind of in the middle of the field and do it, and the robot basically had to do a pull up on the bar. A lot of climbers will use some type of spring to do the extension, and then just use the motor power to really do the pull back in, because you're the only weight you're lifting to push the hooks into the air is just basically the weight of the hooks themselves and the little bit of weight of the bar, of the tubes, and the hardware, the nuts and bolts and things. So it's not a lot of weight when you're actually going up. So these springs right here, these coils, are constant force springs. We saw these a couple days ago when we were looking at the 1114 elevator. They use them to kind of counterbalance. We're using them in a similar idea. This end of this spring, you can kind of imagine it like a really strong tape measure, would be bolted to the bottom of one of these tubes. Let me see if I can make this transparent. So you'd have this bolted all the way down to the bottom of this tube. There'd be a hole and you'd either bolt it or rivet it or something like that, and you'd attach it here. And so if there was nothing else going on in the system, this spring would basically always keep the hooks extended into the air. So they would be really tall. And then what the robot has to do, and what you have to figure out as a team, is how do you kind of retract it back down and hold it back down. So that's where you end up with some type of winch. In this case, they have two Falcon motors into Andy Mark's Sport gearboxes. So these are a different type of planetary. We talked about VersaPlanetaries last year. Andy Mark sells the Sport gearboxes. They're a little bit less configurable than the VersaPlanetary, but they're designed to kind of take greater loads than the VersaPlanetary. So they're really nice in some of the climbing applications. You can do a lot of, you can kind of beat them up a little bit more without them having any of the parts break or anything like that. So you have one on this side that has a sprocket with a modeled belt. There's not a sprocket over here, but we kind of, a lot of times in CAD, if you're looking at other people's CAD, you kind of have to assume things. So we assume there's a sprocket here. We assume there's a hex shaft going through these two hex bearings. And then they don't have anything modeled, but it's very likely, or at least it's not shown right now, it's very likely that there's some type of spool or something like that that would basically have a cable or a cord or rope or something like that that would basically attach to the bottom of this tube that's going all the way up. So when it's wound fully in, you'd basically be holding this tube in against the spring. As you reverse it and kind of let string out, the spring will pull up the hook and let it go all the way out. And then when you go the other direction again with the motor down at the bottom, you get a lot of force pulling down on the hook, and you're able to collapse this telescoping mechanism, and you get the robot in the air if it's hooked onto the bar properly. So that's kind of how it's powered. You do always have to figure out how you're going to build the bearing setup for anything like this telescoping or any type of elevator. So that's what these side plates are for. These side plates hold the bolts. Whoa. I've lost on chip. Okay, we'll let it refresh. Oh. Okay, once we look at the bearing assembly, that'll be the end. We were so close. Maybe. There we go. All right, bearing assembly. So we have these relatively long bolts going through. So these are number 10. These are probably 1032s, and they have these small bearings riding on them, kind of with spacers here. So these are there to locate the bearings on this inner tube, and most of the time you want these bearings sitting pretty close to where the wall of this tube is, because if there is any, when the actual robot's weight's on here and it's trying to kind of bend this whole assembly, you don't want to be able to kind of bend in the open part of this tube. So you really want the bearings riding along this part, the kind of the side wall of the tubes when you can. That'll make the whole assembly stronger. They do that on the front and back, and then side to side, there's a lot less load most of the time. So in here, instead of having bearings that are actually rolling, they just have these plastic blocks that they're basically just using as sliders. So you're going to have a little bit more friction here, but most of the time there's less of a bending friction on the robot since you have the two hooks grabbing on. You're going to be pulling pretty straight in this direction. You're not going to have a lot of you're not going to have as much lean. Plus everything's going pretty slowly. You have two Falcons. There's more than enough power to lift the robot. So having just the sort of sliders instead of bearings probably works totally fine here. It's very possible you could even do that with these other ones too. If you didn't want to have bearings, you could have sliders, but bearings sometimes are even easier. Like these plates and the bearings going through are pretty easy setup. There's nothing too complicated about it. We're getting bearings going the other way is a little bit harder. You have to have another plate kind of under it or something. It just gets a little bit more, it's a little bit more work. So they didn't do it and didn't design it in here. But having some combination of sliders and bearings is totally fine. At the bottom, they have to have a bearing and slider setup as well. Oh, actually, on the other side, we're not hidden, so it'll be easier. We hid parts of it. All right, let's see if we get down into here. All right. So this is just stage one, so we can see this without having to hide a bunch of stuff. So they have these two sliders that are just bolted in to the plates here. So this T plate forms a lot of how they're able to build this bottom assembly. They have bolts going through the two of them that have the bearings for the one for kind of the front and back rollers, and then they just make these plates that bolt into this assembly here. So it's very possible that this is probably aluminum that gets tapped so that those bolts can go through, so there's no nut there. And they just have that bolt assembly with the bearings and everything runs smoothly up and down the inside of the other tube. All right, I think that covers most everything. So there's a couple design choices that they didn't do. So at least in CAD, there's no way, they don't have anything connecting the two sides of their climber hooks. So in theory, these wouldn't necessarily be running exactly at the same spot. It's possible one of these could be higher than the other. It's also possible that doesn't really matter in this game necessarily. So like if you depend, because the bar is going to be kind of at a different angle, maybe you don't really know. So it's not necessarily a bad thing that these may be at different heights. It's kind of just a design choice. The way they mounted these gearboxes, they just connected flat plates across the. There's a single flat plate, this one here, that connects across the AM1ForYou chassis. And then there is a connecting plate on top of the two motors, or the two gearboxes, so they're just connecting those together. That does make it a little bit trickier to bend, but it's very likely if they added either some amount of flanges, so if this instead of was a flat part, if this was an L or a box tube, or if they added some flanges down here to make it a little bit stronger so it doesn't bend as easily, because you will see a decent amount of torque coming through here as the robot's trying to climb. It probably doesn't bend very much. Like you probably get away with it for a long time, but it would be something I would be looking at if I was building this exact design, is potentially strengthening some of these flat parts. That may be with other standoffs through it or something too. There's other ways to do that same type of sort of boxing, or just making that whole structure less flat to prevent some of the bending or twisting. Okay, I think that covers most of this robot. So I think we're gonna call it, oh, the last little bit. So the only thing we didn't really discuss, this will only take a minute, is we do have a couple, kind of just the way their frame structure works for being able to mount the whole superstructure is they just have these two 2x1s running the whole length or the whole width of the robot. And that kind of becomes their mounting points for everything else. So their intake, and all of that gets mounted here. They have one more on this back, or they have a couple more on the back rail acting as risers. But almost everything gets mounted from here. And that's a really nice way to do it on the kit of parts chassis, to start being able to mount everything else. If you just can put a couple beams going across the width of the robot, then you can mount everything to that. Their intake has some pieces of extrusion come up. These could be very easily done with a Versa chassis from Vex, or any of the Rev or Andy Martin gussets. Can all kind of do the same thing. This pneumatic is just here to deploy their intake in and out. So at the beginning of the match, this gets flipped up and is all tucked in inside their frame perimeter, which is defined somewhere about like that edge of the inside bumper, right? So that all gets tucked up in here. And then when the pneumatics deploy, it gets pushed out, and they build the little pivots just using gussets here and here, which works really well. And then the rest of the structure, all of the tower and all of that, gets mounted to those same two bars that are just crossing the whole robot. Okay, now I'm actually finished.